Assalamualaikum warahmatullahi wabarakatuh. I read to all the lecturers. My name is Sabrina binti Maisuf and I am the team leader for group number 3, Petrifier all. As for today, we'll be doing a preliminary presentation on a field development plan for Gelama Merah Field. This presentation will include the reservoir engineering, production technologies, grading engineering, facility engineering, and also economics discipline. We will start our presentations with the reservoir engineering department first.
In this part, the reservoir characterization and the reservoir planning of the Gelama Merah field will be discussed. This evaluation will be used for determination of highest oil recovery and highest recovery factor. The reservoir is saturated reservoir that consists of three different liquid, which is gas, oil, and water. There are 9 layers of sand unit of the surface map, which is U1, U2, U3, U5, U6, U7, U8, and U9. The depth of gas-oil contact and water-oil contact is plotted on the graph. The GOC is found at depth 1495 meter and water-oil contact is at depth 1545. From the ternary diagram, it indicates black oil as phase behavior of the reservoir. From the data gathered by the GNG department as well as petrophysics department, reservoir engineering will be responsible to study the performance of the reservoir. This part will focus on the determination of the oil and gas reserve on the field. Gelama Merah, once its reserve and recovered amount has been decided, we will plan for the well planning to have the best recovery factor. These are the objectives that we should achieve at the end of this part. First one, characterization of the reservoir, reservoir properties, classification of reservoir and hydrocarbon fluid, well planning and bubble map, reservoir simulation, and development plan. In the characterization of reservoir, there is 5 elements that will determine the characterization of the reservoir. The first one, a reservoir geometry, fluid temperature, pressure gradient, and fluid contact. For the reservoir geometry, the reservoir of Gelama Merah field consists of gas, oil, and water. There are total 9 layers of the surface map, which is U1 until U9. The depth of gas oil contact and water contact are plotted on the graph. The GOC is found at the 1495 and WLC is at depth 1545. Based on the observation of the plot, there is no any fault detected. For pressure gradient, the data given we get from MDT, we can plot the pressure graph gradient. The reservoir system contains 3 different layers of fluid such as gas, oil, and water. Hence, we can determine the gas oil contact and water oil contact from the graph. The calculation of the pressure gradient based on the type of liquid. It also can be done based on the equation on the graph. For temperature gradient, Sabah Basin has a temperature gradient in the range of 18.2 to 32.5 degrees Celsius per kilometer. Figures show the temperature gradient of the Gelama Merah field based on the MDT data provided. The calculated temperature gradient is at 35 degrees Celsius per kilometer, which is still in the range. For reservoir datum, the reservoir datum is determined by calculating 1/3 of oil phase zone thickness from the water oil contact. From the depth datum, we can determine the datum temperature and pressure to be used in simulation. From the calculation, the oil phase zone thickness is at 50 meter depth. The depth datum is calculated at 1528.3 meter. Pressure datum is at 2155.53 psi and temperature datum at 84.48 degrees Celsius. For fluid contact, we can see the table 6. At sand unit 1 until 8.1, the fluid phase is gas at 0.52 psi per feet. For 8.2 until 9.1, the there is an oil phase at 0.3125 psi per feet, and for 9.2 there is a water phase at 0.4688 psi per feet. We move to the first reservoir rock properties, which is the porosity. Porosity is the ratio of the pore space volume to the bulk volume. High porosity will result in a larger volume of trapped fluid available between the matrices. Larger porosity will benefit reservoir engineer the most because more oil could be produced, and it becomes the desired location for production well. The porosity value was obtained by the Petrophysics department, and it's classified to three different values. The Monte Carlo simulation proposed the projection of the uncertainty of the porosity in terms of maximum, most probable, and minimum properties. Is water saturation. Water saturation is an estimate of its fraction of or percent to volume of pore occupied by water. Generally, it can be measured by dividing the quantity of water by pore depth. The water saturation value was calculated from the Glamour logging data obtained. The Monte Carlo analysis was performed to determine the minimum, most likely, and maximum of the value. From the table, this is a value we get from the Monte Carlo analysis. It's been determined by a differ of sand unit. We move to poro probability relationship. Probability of the Glamour field is obtained from the core data. By using poro per model, we are able to classify the reservoir rock as in figure below. The measure core probability was within the range of 20 millidarcy, in between K, in between 150 millidarcy and more than 150 millidarcy. And this measurement provided the following transformation of poro probability. There are three types of quality of rock. For low quality rock, K is there are three different probability. The green one is a good, the red one is moderate, and the blue one is poor. From the table, the value of probability we get is from the Monte Carlo simulation analysis. Next properties is rock compressibility. This is important because it is necessary to determine the decrease in pore volume because of the changes in reservoir pressure. Such changes occur because of the increase in depth and the pressure produced from the rock above the reservoir itself. The compressibility of gamma merah on different sand unit is shown in the following table. The compressibility of the rock was determined based on the porosity value calculated by the Petrophysics department. Furthermore, the GNG data form is also used to determine the consolidated sandstone structure of a Newman correlation. As Glamour is consolidated sandstone, the compressibility value will therefore be determined using the Newman 1973 correlation. The equation was proposed compressibility rock compressibility is equal to A divided by 1 plus C times B times theta, and the theta is a porosity. For the table of rock compressibility, the value rock compressibility is calculated by using the Monte Carlo simulation analysis with their different sand unit. the properties of reservoir can be averaged to determine the minimum, most likely, and maximum of the rock properties. The table below shows the average rock properties for the Lama Merah field. So for porosity, the minimum value is 0.14 for most likely at 0.22, and for max value at 0.3. For water saturation, 0.13, 0.43, and 0.79 for respectively minimum, most likely, and maximum. The probability, the minimum is at 120.54 millidarcy, 188.56 millidarcy for most likely, and 256.57 millidarcy for max. For rock compressibility, is at 3.66, 10 power of 96. For minimum, 6.49 to 10 power of -6 for most likely, and 9.32 for 10 power of -6 for maximum value of rock compressibility. From the calculation above, we also get fluid properties to their respective phase for water, oil, and gas. Next, we move to ternary diagram. It is a graphical representation of concentration in a system with three components. This ternary diagram will illustrate the phase behavior of the fluid in the reservoir. Composition of the gas in the reservoir indicates by ternary diagram by using the mole percentage provided in the data given. The composition of light hydrocarbon C1 and N2, medium hydrocarbon C2 to C6 and carbon dioxide, and the heavy hydrocarbon C7 plus is at 28.92%, 5.08%, and 95.99% respectively. Based on the ternary diagram, the phase behavior for this reservoir is the black oil. Last but not least is phase envelope. From the ternary diagram, we have already obtained that the phase behavior is the black oil. From the data collected before, we can obtain the phase envelope using the Eclipse software. The characteristic of the reservoir is the saturated reservoir and black oil. This is due to initial pressure and temperature is located outside the envelope.
We move to 4.6 well planning, number of well. The well planning used to determine the optimum number of well to get the maximum oil recovery. So the table below shows the total production at different numbers of well. So generally, we are expecting for 6 number of well that can give a different number of total production. We've given the for one well we gain the 2.9 million barrel per day. For two we gain the 5.3, 7.5, 12.1, and 15.8, and lastly 17.8 million barrel per day. Okay, from the total production that we gain from the number of wells, we can calculate the recovery factor from the total production divided by the start. So this figure is a craving curve of total production of number of wells. So the number of wells needed and various characteristics were determined using the craving curve approach. From the figure, the ideal well was 5 total production wells because the slope at 5 to 6 is begin to decline. Next is production control. So basically there are two types of production control using in the simulation, which is a flow rate control and bottom hole pressure control. The best way to control production in the reservoir simulation is flow rate control. So the table below represent the total production at different oil rate. So at 900 stock tank barrel per day, the production is at 12.8 million barrel and give the recovery factor at 14.64. So at 1200 stock tank barrel per day, the production is at 13.42 million barrel and give the recovery factor at 15.35%. At 1500, the production give at 14.58 million barrel, and then the recovery factor calculated is 16.68%. At 1800 stock tank per day, the production is at 15.8 and the recovery factor is at 18.08%. And lastly, for 2100 oil rate, give the production at 16.1 million barrel and the recovery factor is 18.42%. So this is a figure for creaming curve of oil production control. The ideal flow rate was 1800 stock tank barrel according to the oil rate creaming curve figure below. The production at 2100 stock tank barrel per day shows a big changes compared to 1800 stock tank barrel oil rate. Consequently, the flow rate at 1800 stock tank per day provided the optimum production control. Okay, next is a bubble map. The best case scenario is based on the natural drive mechanism. So the table below shows the information related for the best case scenario. So basically, in this base case, we are using 5 number of production wells. There is no injection well for base case. The total production is 15.8 million barrel. So we calculate the recovery factors for the base case is at 18.08%, and the oil rate flow rate control we are using the 1800 stock tank barrel per day. In this slide, the figure shows the location of well for the base case. Consists of 5 well placed on the high potential of hydrocarbon production. Okay, in this table, it shows the coordinate location of the well for the base case. There are 5 wells for production wells. There is a drill depth. There is a formation or perforation depth that we produce. So the X and Y location, this location actually we get from the Petrifier software. We move to 4.7, reservoir simulation static model. The static model of the reservoir can be determined by using the several computer software such as Eclipse and Petrifier. So the figures shows the 3D diagram that being generated by Petrifier software. So for production profile, we have generate the production profile for the base case. So the production of the base case well is around 10 years. So the y-axis at the left side is referring to oil and water in stock tank barrel, and y-axis at the right referring to gas in million scuff. The total production of oil and gas water is 15.8 million barrel. For gas, 173 billion scuff and 6 million stock tank barrel respectively.
Assalamualaikum and hi, my name is Sofia and I will continue to discuss on production technologies department. In this department, we will focus to maximize the production of oil and gas in a safely and cost-effective manner. The elements that we'll discuss in details in this department is related to maximize the production, such as well completion design, artificial lift requirement, material and size and tubing size selection. The data used in this department were taken from other departments, especially reservoir department, and also the data from well test report given. All the elements that we'll further discuss in this part has its own objective, which is to provide a safe, effective, and also economically viable design of a well completion for all the producers in the well completion part. And next, in the size of tubing selection, is to maintain the well integrity throughout the production life, together with having the maximum production, and also to have a future well intervention and recompletion for any production enhancement activities is in the artificial lift part and also production problem part. These are some of the data that were collected from other departments, such as J&G department and reservoir department. As we can see here, the stock value is 87.41 million barrels with the recoverable stock, which is 15.8 million barrels. That means the recoverable factor in this field is 18.08%. And from the reservoir department, the static model is expected to have a production rate per day, which is 1,800 barrels per day. This is the plan and strategy for the whole production technology department. We will start with the well performance analysis by analyzing the IPR and TPR with several sensitivity analysis, and then proceed with well completion design and artificial lift consideration, as well as the sand production prediction and sand control strategies by reviewing the core data. And then we will proceed with the potential production problem identification before we design the final model of the development. The first part is well performance analysis. By having this analysis, we can decide the optimum tubing size for the well. The method that we use is Vogels method using pipe sim software. Why we use Vogels method? This is because the reservoir pressure of the well is higher than the bubble point pressure, as well as the bottom hole pressure is lower than bubble point pressure. That means this field is a two-phase reservoir. One of the consideration in deciding the size is to have a maximum production throughout the field life. In order to decide the optimum size, we did several sensitivity analyses, which are reservoir pressure depletion, water cut, gas oil ratio, and well head pressure. The produced oil rate expected by the tubing need to achieve the expected oil rate that we have decided before, which is 1,800 barrels per day. As we can see, this is the present IPR and also the future IPR. The future IPR is same as the sensitivity analysis with the pressure depletion. This is the future IPR for the 4-inch tubing size. And this is the first sensitivity analysis that we did, which is using the different sizes of tubing. The range of the tubing size is start with the 3.5 inch, followed by 4, 4.5, and 5 inch. And as we can see here, the IPR is the same IPR as before, and the TPR is using the different sizes of tubing. Most of the tubing manage to achieve the expected oil rate from the reservoir, which is 1,800. However, after having after analyze the whole sensitivity analysis, we decide to have a 4.0-inch tubing size, because all the sensitivity analysis are able to produce the 1,800 expected oil rate. The next sensitivity analysis is gas oil ratio. The range that we use is 336, followed by 416, 496, 576, and the last one is 600 scarf per XTB. This is the expected range from the production profile by the reservoir department throughout the life cycle. Still, the optimum size of the tubing selected is still 4.0 inch because the expected oil rate by the tubing the expected oil rate produced by the tubing is not having much difference, so we decide to choose 4.0 inch to reduce the cost. The next sensitivity analysis is wellhead pressure, and this is the wellhead pressure at 250 psia for the whole for the different sizes of tubing, and the wellhead pressure that we use is 390, 250, and also 110. In this slide, this is the details well deliverability results, which is the first table is the operating point for the different tubing size. Our selected tubing size is 4.0 inch. The next is the first sensitivity analysis, which is the water cut. We decide to analyze the water cut starts from 0% until 80%. However, during the 60% of the water cut, all of the tubing size are not able to produce any oil at all. And this is the next sensitivity analysis, which is the gas oil ratio as well as the wellhead pressure. This is the details result for the well deliverability. This is the last sensitivity analysis, which is the reservoir pressure. As we can see, the reservoir pressure will affect the IPR. At the end of this part, we have decided that the selected optimum tubing size is 4.0 inch. Although at the 1700 psia, it will not be able to achieve the expected oil rate. That means in this moment we will having the artificial lift consideration to have a maximum production rate. The next part is artificial lift consideration. We have decided that the selected artificial lift that we will use is continuous gas lift. From the reservoir characteristic point of view, we can select the ESP because it requires the minimum tubing diameter for ESP is 4.5 inch outer diameter. Since before we have decided the tubing that we will use is 4.0 internal diameter, so it is well suited for the gas lift implementation. From the point view of operational problem, it is less operational problem due to the having fewer moving parts. The next one is from the point of view of economics. It can be used up to 10 to 20 years. So since our life of production is about 10 years, it is economically viable to use gas lift other than other artificial lift method. The subsurface of gas lift equipment is also relatively inexpensive, as well as it requires low cost compared to ESP. This is because the ESP require frequent change, and it needs to maintain by time. By implement the gas lift system, it is suitable for our reservoir because our reservoir will produce sands. The next part is the material selection part. This part is important to ensure the completion longevity. These are the parameters that use in order to select the material. As we can see here, the concentration of CO2 that we use is 2.85 percent, and the concentration of H2S is 0%. The reason why we choose 2.85% of CO2 concentration from the well test report is because we take the worst case scenario in order to select the best material. From the calculated PCO2 and PH2S, we can see that the PCO2 is 4.14 bar, which is higher than the 0.2 bar from the chart. And then we can see that the PH2S of the PH2S is 0 ppm. So it is lower than 0.003 bar. And for the temperature of the reservoir, it is 68.3, so it is lower than 150 degrees C, if I'm not mistaken. So it is decided that we choose the SM13CR kind of material. The SM13CR is the martensitic stainless steel. It is suitable for sweet environment under condition which the carbon and alloy still suffer localized corrosion. The SM13CR also can offer high strength material and improve corrosion properties and larger application. The next part is the perforation technique for this well. The selected perforation technique is tubing convict perforation system for this Glamour Merah field well. This method is chosen because of the flexibility and cost-effective working technique, as well as to save the rig time by perforate long intervals in one single trip. It is also have a various application of diameter, length, and shot density. As evidence from the DSC results, it proves to be effective with the negative skin of negative 0.1 skin for this well. Next is the completion and packer fluid part. For the completion fluid, it is preferred to use the clean brine compared to mud due to salt ability to go into the solution rather than having suspended solid that may settle after a long period of time. This clean brine also chemically compatible with the reservoir formation and fluid for this well. The next one is for the packer fluid. It is advisable and preferable to use the treated brines for the Glamour Merah field. This selection is based on the several factors including the pressure control, corrosion properties, availability, and the cost of the fluid. The last part for this production technology department is the potential production problems. The first problem that we have is the near wellbore restriction that caused by the decrease in permeability and emulsion. To control those problems, we can reduce the relative permeability by implementation of hydraulic fracturing to the reservoir. We can also break the emulsions by using the special and specific demulsifier agents for this well. The next problem is corrosion. Based on the PVT report, we have the CO2 content which is 2.85%. It is enough to expect the downhole corrosion will happen in the presence of the liquid water in Glamour Merah well. So to control those production, we introduce and use the 13 chrome material as it will offer enough corrosive resistance to the downhole equipment and protect the surface pipeline and fittings. The next problem is liquid loading due to the insufficient of pressure difference from the reservoir pressure to the wellhead pressure. To cater those problems, you can install the artificial lift as we decide. before this, which is the continuous gas lift to lift up the liquids to the surface. The last problem is the mechanical failure. The examples of the mechanical failure is parted rod, stuck pump, casing leak, as well as the plug leaking. To control those problems, we can establish a proper maintenance as well once the production is made uh, throughout the production life. Finally, you have come up with the conclusion for this production technology department. We can conclude that the Glamour 1 field is a two-phase reservoir since it has reservoir pressure that higher than bubble point pressure, as well as the bottom hole pressure is lower than bubble point pressure. So for the well deliverability using the PipeSim software, we can use Vogel's method. From the well deliverability part, we have select the tubing size, which is 4.0 inch. And the selected artificial lift is continuous gas lift, as it is more economically viable compared to ESP. For the material selection, we have select the SM13CR to cater the corrosive part, since we have CO2 percentage which is 2.85%. For the perforation technique, we have select the tubing conduit perforation for this well. So I think that's all for the production technology department. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and a very good day. My name is Muhammad Nur Azmi bin Muhammad Azli, and I am a person in charge for drilling engineering department for field development plan FDP for this semester. So, the drilling engineering department's targets are to design an effective drilling program and to propose a suitable drilling waste management, drilling risk, and its mitigation plan, and abandonment by coordinating with other departments. So we move on to rig selection. For rig selection, there are three types of rig that are being considered. The first one is jackup rig, the second one is tender assisted rig, and the third one is semi-submersible rig. The table shows the depth in feet, average daily cost estimation in USD, and availability for each rig. So jackup rig is chosen for this drilling program as it reasonably complies with all the required aspects. Jackup rig is cost effective due to its lowest average daily cost estimation, and it is also have low maintenance costs due to its simpler wellhead assembly and less downtime. And jackup rigs have the highest availability, so it is easy to procure the rig. So the next one is spider plot. So as you can see, the graph shows the spider plot for wells for base case. Three cases were proposed to achieve optimum recovery. Comparison has been made between the three cases, and base case has been chosen as it shows a higher recovery factor of oil production. The next one is casing setting depth. So the pressure profile was plotted based on MDT data obtained from the GM1 exploration well. The pressure profile indicates the formation pressure, probe pressure, and overburden pressure that normally exerted in the Glamour Merah field area. The Eaton method was applied to determine the fracture gradient of the pressure profile. So the graph here shows the pressure profile. Pressure in PSI is plotted against depth in meter. There are four sets of data is being plotted, which are pore pressure, fracture gradient, kick margin, and trip margin. So from pressure profile, it can be determined that the conductor casing setting depth is at 360 meter. For surface casing, the depth is about 550 meter. For intermediate casing is about 870 meters, and for production casing is about 1504 meter in depth. The most important thing in casing design is that the chosen casing grade must be able to withstand the external pressure in the wellbore formation and internal pressure. Thus, collapse load, burst load, and tension load were calculated. Tension load is known as the maximum pressure that the casing can withstand during running and pulling out operation of the casing. The casing specification is chosen based on highest pressure containment and cost effectiveness. The design factors are included as a safety precaution for all the casings in sustaining the resistance exerted inside and outside of the casing. The table here shows the load and the design factor used. So for burst load, design factor is 1. For collapse load, the design factor used is 1.1 and tensile load is 1.3. So the table here shows the summary of casing design for each casing. So for each type of casing, the grade, the outer diameter in inch, internal diameter in inch, hole size in inch, nominal weight, and wall thickness in inch are stated clearly. So lastly, as a conclusion, jackup rig has been chosen for drilling rig. The casing setting depth for each wells are 360 meter for conductor, 550 meter for surface casing, 870 meter for intermediate casing, and 1504 meter for production casing. The grade and hole size chosen for each casing are J55, 26 inch for conductor, L80 and 17 half inch for surface casing, L80 12 and quarter inch for intermediate casing, and L80 8.5 inch for production. So that's all from drilling engineering department. Thank you.
Assalamu alaikum and a very good day. My name is Muhammad Alif Haikal bin Izani and I am the person in charge of the Facilities Engineering Department for the Field Development Plan for this semester. So the objectives of Facilities Engineering Department is basically to design the oil and gas production facilities as well as to decide on for the most suitable oil rig platform for the development of Glama Merah field by taking the data obtained from the Reservoir Engineering Department, Drilling Engineering Department, as well as the Production Technology departments into considerations while making the decisions for these departments. So basically Glama Merah 1, or also known as GM1, is in a block off the coast of Sabah, which is in the Sabah Basin in Malaysia. The water depth of this field is 42.8 meters, and as you can see from the figure, the field, Glama Merah 1, is also nearby to the Samarang platforms, where SMGA being the nearby existing central processing platform that is approximately 13 to 20 kilometers from GM1. Moving on, as we know, the well will be producing all three phases, which is gas, oil, and water. Hence, the processing unit has to accommodate to process all these three forms of hydrocarbons. and water. So for the proposed PFD, processing PFD, the processing unit should include separation processes to separate all three gases from the liquids, as well as the oil from water. And there's also a need of oil storage compartments to handle the oil that has been separated from the other components. And since there is also water, there is also need of the water treatment processes, so that the water could be processed to meet certain requirements, certain specification, before some of them will be discharged into the ocean water body, or even to be used as utilities for other processes. And as for the gas, since there is gas, there's a need of gas processing units or equipments, so that the gas could be handled safely, and the gas that needs to be flared shall be flared, and the gas that should be processed or stabilized will be stabilized and processed. And all these are required because before the processed hydrocarbons could be transported to the Labuan and terminals, the hydrocarbons itself need to be processed to meet the requirements of the Labuan terminals. So moving on to the development concepts, Facilities Engineering Department has proposed 3 different concepts to develop Gelama Merah 1 field. So the first concept A, consists of a fixed jacket, which are built by having a 4-leg jacket structure, and the platform is an integrated platform where the wellhead platform, CPP platform, central processing platform, as well as the living quarters and other units will be on one same platform. And as you can see from the figure shown, once the hydrocarbons has been processed, they will be transported via built pipeline to the Labuan terminals, namely Alcod for the oil, Algas-T for the gases. Moving on for the next concept B, the proposed concept basically consists of by having only the wellhead platform that is going to be built, which is also a fixed jacket that is constructed from a 4-legged jacket, and the platform is only a wellhead platform, WHP platform, which means that these platforms specifically will be only involved in the production activities, where after that the produced hydrocarbons, all the 3 phases produce liquids will be transported to the existing central processing platforms in the Semarang fields, or also known as the SMGA platform. So basically the processing operations will happen on the Semarang central processing platform before it could be transported via the existing pipeline to the Labuan terminals. And last but not least, the final concept proposed, the concept C, is basically the FPSO, which consists of a tanker and an integrated platform, which also works from where the integrated platform will do everything from production activities to the processing, as well as it also has the living quarters on the tanker. And once the hydrocarbons has been processed, it will also be transported to the Labuan terminals via pipeline. Moving on with the economic evaluation, we will be comparing all three concepts in order to finally decide on which out of the three is the best option. So as you can see from the total capex, the total cost, concept B proposed the lowest cost, as well. One of the major reason is that we only gonna build the WHP, the wellhead platform, for the production activities, as well as the transportation line from GM1, which is the wellhead platform, to the existing CPP SMGA, while the other are already existing, hence the costs are neglectable or just very low, as the only costs that might be included are maybe some upgrades. And as you can see, concept B would be our final decisions to go forward with this field development, as it is the most economically viable concept. So as a conclusion, the final concept is chosen by taking all the advantages and disadvantages, as well as the risk and the economics, into consideration. Hence, the final concept, as I mentioned before, is concept B, which is a wellhead platform with the tie-ins to the existing Semarang CPP SMGA, and the produced hydrocarbons will be produced by the wellhead platform itself, and then the produced hydrocarbon shall be transported to the existing CPP to be processed before it could be transported to the Labuan terminals, which is LCOT and LGAS-T respectively. So the main reasons for choosing this development concept are as following. Of course, because of the lowest total capex, which make it the cheapest strategy out of all the other strategies. And as we know from reservoir engineering and production technology departments, this concept is also viable and economically viable, because the production rate is basically approximately 1,500 million barrel per day, which is, according to the experts from Petronas, is considerably low to be, to even consider building a totally new integrated platforms, or to spend so much that it could pose not to be so economical. Hence, concept B is by far the best options as compared to the other strategies, as the other options.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nasabrina binti Maisuk, and I am the person in charge to lead this economics department. So to begin with the presentation, we'll first see the objective of this economics department. The objective of this department could be divided into four main objectives. The first one is to make certain economic assumptions based on the current economics. Second is to summarize the technical input from the drilling, engineering, facility engineering, and also reservoir engineering, so that the cost and revenue can be identified. Third is to analyze the profit that will be generated by the project based on the net cash flow, net present value, internal rate of return, and also the profit investment ratio. And the last one is to determine the robustness of the project by studying the risk and sensitivity analysis of the Gelama Merah economics. Okay, this slide shows the summary of a reservoir planning proposed by the reservoir engineering department. So this is very important, as we wanted to know which cases that produce highest oil productions and also recovery factor. So from this table, we can see that base case contribute to the highest oil production with the 15.8 million stock tank barrel. Next, moving on to the drilling planning. This is the table showing the summary of drilling planning proposed by the drilling engineering department. So they proposed three options. The first option using the jacket rate. Second option is using the tender assisted rate, and third option using the semi-submersible rig. And for the rig type selection, it will be based on the cost, the suitable with the condition of the field, and also the availability of the rig. So based on the cost, option 1 will be chosen as it has the lowest uh, every daily cost estimation, and also it is um, suits to the glamour merah field condition. Next is the facilities planning. So facilities department has proposed three options for the facilities planning. The first option is the integrated platform. Second option is the wellhead platform tying into the existing Samara central processing plant, and the third option is using the FPSO. So from the total cost, we can see that option 2 is the best economical viable since it has the lowest total cost, and this option 2 will be proceed with the best facilities planning. For the economic evaluation of glamour merah feed production, our group has decided to apply the production sharing contract PSC 1997 for the splitting profit. So the basic principle of this PSC 1997 revenue over cost is to permit the PSC contractors a higher share of production when the profit is low, and it increase the Petronas share of the production when the contractor's profit is improved. So the details of the fiscal term of PSC is tabulated based on this table. So the royalty is 10% of the revenue. Income tax is the 38% of the taxable income. With the supplementary payment for oil is 70% of the oil recovered, and the supplementary payment for gas is 60% of the recovered gas. The export duty, 10% of the oil profit. Exploration period is for 3 years, development period is 4 years, and production period is for 20 years. Next, there is the economic assumptions. So the assumption for oil price is $51.5 per stock 10 barrel. Gas price is 2.49 US dollar. The reference year is in the year of 2020. Production year for 4 years, and the escalation rate is 3% for actual oil price, 6% for base oil price, and also 5% for OPEX and CAPEX. Next is the company economic indicator. The hurdle rate is 17%, profit investment ratio more than 1, and the period for payback is less than 8 years. This graph shows the EIA price projection. It shows the price projection of the oil price and also gas price from the years of 2020 until 2038. So this slide shows the technical input of CAPEX. For the analysis of CAPEX for each of case, it can be divided into 5 categories, which is the fixed structure cost, topside cost, decommissioning cost, intangible cost, and also tangible cost. So from this table of capital allocation for every case, we can see that base case has a total estimation of $151.71 million, case 1 $290.41 million, case 3 has a total estimation of $291.25 million, and case 3 with $297.11 million. So from this capex, we can see that base case has the lowest total estimation cost. The next technical input is OPEX. So there are two types of OPEX, which is the fixed OPEX and also variable OPEX. So to calculate the fixed OPEX is 5% of the capex, and variable OPEX is $0.5 per STB if multiplied with the oil production. So the table below shows the um, total OPEX for each of the cases. Okay, moving on to next technical input, which is the capital allowance. So capital allowance in this project was divided into three sections, which are 10% straight line for fixed structure, 20% initial, and 8% annual allowance for topside, decommissioning, and also tangible items. And third one is the capital allowance for intangible and exploration is 100% write-off. From this table shows the summary for capital allowance for each cases from the years of 2023 until year of 2037. Moving on to the cost estimation. It is a measurement of the investment of a project to the ratio of oil produced. The smallest value of a cost estimation, the less investment need to produce one total barrel of oil. So cost estimation can be divided into four, which is the unit finding cost, unit development cost, unit operating cost, and also unit technical cost. So based on the table below, it shows the project cost estimation for each of case. We can see that case 1 show the lowest UTC value, which indicates less cost incurred to produce an oil. In conclusion, the fiscal term that we choose for the Glamour Merah field is the PSC 1997 revenue over cost. Next, in the well planning reservoir summary, the base case has the highest oil production and recovery factor. And the last one is for the project cost estimation, case 1 has the lowest UTC value, which indicate the less cost incurred to produce an oil. However, to have a better economic analysis, we need to do the economic model, which is still in progress. That is all from our group for the preliminary presentation. Thank you.